Hi, everyone. I'm 𝗺𝗲𝗱𝗶𝗶, a systems performance engineer here at Micron on the data center workloads engineering team. And today I'm going to talk to you about MLPerf storage version 1.0, which just published the set of results. Now, if you've followed any of my other content, blog post, or conference proceedings, you'll know that storage for AI is a broad and complex topic. There are a lot of places in the AI pipeline where storage is important. Today, though, we're going to focus specifically on data ingest for AI training. Two of the specific issues that we need to overcome to be able to benchmark AI training systems, though, the first is AI accelerators are expensive. And if we want to show off a storage system that can support dozens or hundreds of accelerators, that quickly just explodes the cost of the system. The other issue that we need to overcome is that the available data sets are small compared to the data sets used by industry. So for example, if we look at the DLRM V2 model that's part of MLPerf training, that's a recommendation model. The data set that's used to train that for MLPerf training is the Criteo ClickLogs data set. It clocks in at about 1 TB of data on disk in the raw format, and then it gets post-processed down to about 300 GB in a very optimal format for ingest. However, if we read Meta's paper, Understanding Data Storage and Ingestion for Large-Scale Deep Recommendation Model Training, we see that Metastate's training jobs are 10 petabytes to 100 petabytes of semi-processed data per training run. So we're off by a few orders of magnitude. So MLPerf storage sets out to solve both of these problems. The first it solves by emulating accelerators. So we analyze the real training job and pull out the specific parameters and characteristics that describe it and enter those into the emulation system, which is using the same framework, so PyTorch and TensorFlow, the same data storage technologies as the real system, but we're able to run this on CPU-based systems. From the data set perspective, the underlying program for MLPerf storage lets us generate synthetic data sets of up to an unlimited size that keep a lot of the same properties as the original data set. Now, I am going to have a future blog post where I dive deeper into the three specific workloads that are part of MLPerf storage version 1.0. That's just sort of a quick teaser. Stay tuned for that. It will really show why these three specific workloads are worth running, how they're unique from each other, and how they don't necessarily represent what we would expect to see. Awesome. So I'm going to cover our MLPerf Storage 1.0 submission results, which just got published today. And I'm going to go through each of these three workloads, CosmoFlow, FresNet, and UNet3D. And in the top bullet here, I list sort of the configuration of data and how that's ingested. So CosmoFlow is an HPC training application, and it uses the TensorFlow framework and TF record file format to store its data. We use one sample per file, so each TF record file correlates to one sample, and samples are about 4 megabytes in size. Here we see that the performance-focused 9550 NVMe drive supports up to 20 A100 accelerators and 13 H100 accelerators while maintaining a high accelerator utilization. The 6500 ion capacity-focused NVMe drive supports 16 A100s and 9 H100s. This means that for pretty much any existing architecture where you're using local NVMe, the capacity-focused or the performance-focused NVMe drive will both be able to fulfill all of the needs of that system. The next workload is ResNet 50. And if we look at this top bullet point here, we see a couple big changes from CosmoFlow. So this is still using TensorFlow to read in data, and it's reading from TF record files. But the sample sizes for ResNet are significantly smaller. So these are 128 kilobytes per sample, which means we need to pack more than one sample per file. Otherwise, we end up with 100 million files on our file system. So here we've got 1,250 samples per file. The I/O load for ResNet 50 is a little less than for CosmoFlow, so we see some pretty high accelerator numbers for both of these drives. The 9550 supports up to 115 A100 accelerators and 58 H100s, while the capacity focus is still supporting 72 A100s and 37 H100 accelerators. Clearly, both of these drives are going to support any accelerators that you can put into a local system, and what we will likely see these used for resident is more of a scale-out storage solution. The final workload is the most I/O intensive of the three that MLPerf Storage 1.0 supports. In this top bullet again, we see that instead of TensorFlow, we're using PyTorch to actually read in data. And the container format is no longer TF record. We're using compressed serialized NumPy arrays, so NPZ files, if you're familiar with those. We're back to one sample per file because these samples are honestly enormous, 142 megabytes per sample. This does drive extremely high I/O throughput for each emulated accelerator, and the 9550 is only able to support 8 of the A100s or 4 of the H100 accelerators. The 6500 ion capacity-focused NVMe does drop those numbers slightly further to 3 A100s and 1 H100. Now, what's great about this is the capacity NVMe is still supporting 1 H100, which means a one-to-one relationship. And if you look at most architectures out there today, you are averaging one NVMe drive slot per GPU. So for these very I/O focused workloads like UNet 3D, the capacity focused 6500 ion is still going to enable you to train at high rates to enable high accelerator utilization. Click the link below for the full tech brief where we dig into each of these workloads and talk about the samples per second that are supported, as well as how much throughput we're actually achieving out of each of these devices. Be sure to click like and subscribe. Thanks.